Swayam Prabha. Digital India. Educated India.
So I will wrap up NP completeness with a few more examples. So first let's take stock of what are the kind of problems we showed NP complete. We looked at covering problems. So there are different kinds of problems we showed NP complete. So here, for example, vertex cover, feedback vertex set, assuming you did it in the problem sheet, set cover, and then there are problems like a subset satisfying some property inside. So maybe it's like, I don't know how to classify this, but let's, here I would call independent set, click, 3-dimensional matching, which you may or may not have seen it. Then there are some problems where we are the solution is actually looking for a permutation. So traveling salesperson problem, Hamiltonian cycle, Hamiltonian path, these kind of problems. And then there are numeric problems where you have some numbers, and this is where I was last time. We were looking at subset sum and knapsack. Okay, so I mentioned about this Cook-Levin theorem in 1971, which showed that the satisfiability problem, that should come somewhere, is NP complete. But after that, this area opened up, and now there are literally about hundreds of problems which are NP complete in many different areas, geometry, in algebra, various kinds of areas where there are problems which are hard. So this is just a sample of some problems we have seen, and some more in your problem sheet. And with respect to subset sum, what did we see last time? We said, okay, what is the problem? You are given a set of items, each item has a weight, and you have a target weight, and you want to find out, is there a subset of these items whose total weight is exactly equal to W. Okay, the maximization version would be, what is the maximum weight you can achieve if you can't achieve equal to W. And we said if there are n items, then there is a trivial 2 power n times n algorithm, run through all possible subsets, add their weights and see whether that's W. We also saw a dynamic programming algorithm which actually takes n times W, where W is the target weight. So neither of these two algorithms is a purely polynomial time algorithm, because this is exponential in n, this depends on the value and the size of the encoding. When I am encoding W, actually I will use only log W bits. So a polynomial algorithm should be polynomial in n, m and log of the capacities or the weights. Okay, and this is not surprising. We don't expect polynomial time algorithm, because I will show now that this problem is NP complete. Okay, so if I want to show that something is NP complete, first thing I have to show is it is an NP. So there is a witness, a proof for the S answer, which can be verified in polynomial time. So what would be a proof? A subset of vertices that adds up to W. That if the answer is yes, that means there is some subset that adds up to W. So that is a witness, and you add the weights, and that's a verification algorithm. Okay, so it's an NP is easy to see. To show it's NP hard, right? NP complete means it's NP and NP hard. To show NP hard, I am going to pick a known NP hard problem and reduce to this. So, the problem I am going to use is 3SAT. 3SAT is typically a fallback option. If you don't know what kind of problem you want to reduce this from, usually you can try from 3SAT. So, I am going to give a reduction from 3SAT to subset sum. Okay. So, what is the input to the 3SAT problem? You are given a formula which is a conjunction of clauses. So, there are m clauses and there are on variables x1, x2, xn. Each clause is a conjunction, it's a R of 3 variables. Okay, it's a 3SAT, that's why, right. So, from the formula, what do I have to now produce? An input for subset sum. What is an input for subset sum? A set of numbers, exactly, right. I want to produce a set of numbers and a W, a target W, that's my goal, right. So, I am going to produce a set of numbers and a target W such that this formula is satisfiable if and only if there is some subset of this set of numbers that adds up to W. So, the set of numbers I am going to have number of we will have 2n plus 2m numbers. I will write those numbers in decimal, each of length n plus m in decimal. Okay. So, if I have a decimal number, let us say it takes some 5 digits. If I want to convert it in binary, how many digits will it take? Let us say I take each of the digits and convert them in binary. Okay, there are some carries and so on, don't worry about it. Suppose I take each of the digits and convert them in binary, and if I have a 5-digit number, how many digits now it will become? Each number, when I write it in binary, how many bits will it take? 4, roughly 4 bits, right, 4 bits. So, 5 into 4, 20 bits. So, there is a constant multiple, that's all. That's the whole point, right. So, whether I write the number in decimal or binary, it does not matter. Writing it in unary matters, that is a problem. Okay. If you write it in binary or ternary or decimal, there is a constant factor multiple in the length. Okay. Okay. So, how are these numbers looking like? So, I will tell you how the numbers look like. So, let us say, so the numbers are of length, I said n plus m, right. So, one for, so the so I will have a position for so this is a position of the numbers, right. Each number is an n plus m decimal number. So, it has so many digits, n plus m digits. Okay. I am going to write 2 n plus m numbers. So, let us write these numbers as V1, V1 prime, V2, V2 prime. So, there are the number of numbers I promised is something like 2n plus 2m. So, 2 for each variable and 2 for each clause. Okay. So, at the moment it will look like a magic why I am producing these numbers here, but when we come to the proof you will see why the numbers are looking like this. So, V1 will look like this 1 0 0 0. So, V1 will correspond to the variable x1 and V1 prime will correspond to the variable x1 bar. Okay. So, and in this number, this is a big number, right, n plus m digit number. At the x1th position I will have 1, and if V1 appears in whichever clause V1 appears in, I will have some 1 here, okay, and otherwise it is a 0. And similarly for V1 prime, I will have 1 0 0 0 here, and whichever clause x1 bar appears, I will have corresponding 1 here. So, let us maybe do an example. So, let us say I have a clause C1 which is x1 or x2 bar or x3, and I have a clause C2 which is x5 bar or x4. Okay. So, then V2 will have 1 at this position at for variable x2, 0 everywhere else, and then V2 appears as a negation in C1. So, here it will all be 0, but V2 bar will have 1 here, and since it is appearing in C1, it will have 1 here and so. Okay. So, is it clear how I am going to draw the 2n numbers first? Number of numbers is 2n plus 2m. The 2n numbers, 2 for each variable. So, V1 will have 1 here and V1 prime will have 1 here, the x1th position, and whichever clauses x1 is appearing, I am going to have a 1 here, and whichever clauses x1 bar is appearing, I am going to have 1s here, right, because this set of numbers is derived from my formula. Okay. So, that is the 2n numbers. Now, I will tell you 2 clauses corresponding to each clause, 2 numbers corresponding to each clause. So, let us call this some S1 and S2. So, S1 will have 1 in the C1th position, and S2 will have 2 in the C1th position, and everywhere else there will be 0. And similarly, let us call this S1, S1 prime maybe. S2 will have 1 in the C2th position, and S2 prime will have 2 here. That is my set of numbers. Okay. Given a set of variables and clauses, I have produced you a set of 2n plus 2m numbers, decimal numbers. These numbers are, the length of the numbers is n plus m. Any questions on this? Are the numbers clear? Yes. So, for every variable, if it is a variable xi, then there will be vi and vi prime. Vi will have 1 in xi and vi prime will also have 1 in xi. In addition, wherever clauses vi is appearing, I will have 1 there. Wherever clauses xi bar is appearing, I will have 1 in the vi primed position. That is a set of 2n numbers corresponding to n variables, and then 2n numbers corresponding to m clauses, 2m numbers corresponding to m clauses are looking like this, right. So, now I have produced you an input for the subset sum problem from the Boolean formula. Not quite, I need to produce you something more for the input for the subset sum, W. I have to give you a target W, right. So, my target W is simply 4, 4, 4, 4, 4 of length n plus m. Okay. So, given a Boolean formula, I have produced you 2n plus 2m numbers, a set of 2n plus 2m numbers, each of length m plus n, think of them as decimal numbers. And now I ask the question, is there a subset of these numbers that add up to 4, 4, 4, 4, 4, 4, 4, 4 n plus m digits? Okay. Now, the question, so what do I have to show? That this formula is satisfiable if and only if there is some subset that adds up to this number. Okay. Why this 1, 2 and why 4, 4, 4? When I get to the proof, you will see what is happening, right. So, sorry, it is not 4, 4, 4, 4. 1, 1, 1, 1, 1, 1, 1 and then followed by 4, 4, 4, 4. So, the first n of them must be 1, the remaining m must be 4. Okay. So, let us come back here. So, first of all, what is the maximum number you can have in any position, in maximum sum? Maximum sum you can have in any position. Sorry, no, let us just take one position, let us say C1. Okay. Suppose I take all the numbers, what is the sum? In that position, what is the number I can get? 3 variables, right, because C1 is a 3-sat formula, C1 has 3 variables. So, in those corresponding variables I would have had a 1 1 1, and then this one and this 2 together I will get a 6 here. So, in the clause positions the maximum sum I can get is 6. In the variable positions maximum sum I can get is 2, right. Okay, let us keep that in mind, right. In the clause, and there are no carries going over because the maximum sum is only 6 and I am talking about decimal numbers. Okay, that makes life easier. I can just look at position by position. So, now my target sum is 1 1 1 1 1 followed by 4 4 4 4 4. So, if I have to get 1 in an xi position, how can I get it? You have to pick Vi or Vi bar, exactly one of them. Good, right. This gives me an assignment, right. In an assignment I want xi or xi bar, that is why I have set my target to be 1. Okay. Is that clear? So suppose there, so basically I am talking about a reverse direction. Suppose there is some subset of these numbers somebody managed to give which adds up to this number, then in the xi's positions they all add up to 1. So, that means every variable, I mean I would have picked a Vi or Vi prime for every I exactly, right. So, that Vi's will correspond to my assignments. Now, let us get to the clause positions, right. I want a target of 4. Can I get 4 by just looking at the SI's alone? If I, in a column of CI, these SI variables that correspond to clauses can at most give me 3. How do I get 4? I have to have at least 1 from the variable, guys. So, that means that that clause must have been satisfied by one of the variables you have picked. So, let me just go over the both direction proof. I mean, why did I pick 1 and 2? I could have put 3 alone here. There is a reason why I picked 1 and 2, right. I could have just picked one row with a 3 here, which also would have forced me at least 1 from here, right. But there is a particular reason why I had these 2 rows. Why? So, in the forward direction, let us go through the forward direction. Suppose you have a satisfying assignment, right, for the entire formula. That means there is an assignment which sets the variable 0 1 such that every clause is satisfied. So, let me pick the corresponding rows, right. Suppose x1 is 1, I will pick this row. Suppose x2 is 0, I will pick this row and I pick the corresponding rows up to this point. Okay. They will all add up to my xi's will be 1, that is great. Now, I have to pick my Si prime to get my target of 4. So, I go to a particular class C1. Whatever I have picked, since it satisfies C1, at least you would have gotten a 1 from here. What are the 3 possibilities you could have gotten from here? 1, 2 or 3, because maybe 2 variables satisfied, maybe 3 variables satisfied, right. I want to have a room for all the 3 possibilities. So, if you picked only 1, if so happened that in CI only 1 was satisfied, I will pick S1 and S1 prime to get my target of 4. If I got 2 from CIs, I will pick my S1 prime to get a target of 4, and if you got only 1, I will pick both to get my target of 4. End of proof. So, just let me write down the proof, not the proof, the statement. So, F is satisfiable if and only if there exists a subset of the 2n plus numbers that add up to So, basically we have encoded 3SAT into the subset sum problem. I mean, this also shows that knapsack problem is NP hard, because I could have a knapsack with this capacity and I will pick up these numbers and then I will see what is the maximum I can get. If I can actually maximum I can get W, then I know it is satisfiable. If it is satisfiable, I can get W. Okay, good. So, hopefully you got enough experience. I mean, I still don't think that you can just pick an arbitrary problem and prove it NP hard, but at least you will know what needs to be done, right. At least I want that message to get across, that if you want to show a problem is NP hard, pick a known NP hard problem and take an input of that problem, convert it to an input of this problem, so that S goes to S, no goes to no. Now, so I want to just summarize what we have done. So, we have shown that there are these problems which are NP hard. What is the consequence? If any one of them has a polynomial time algorithm, then all these problems have a polynomial time algorithm. If any one of them has no polynomial time algorithm, then none of them have a polynomial time algorithm. Now, I already mentioned in the beginning when I started NP hardness, why do we care about polynomial time algorithms versus exponential time algorithms, right? We saw some example between an n cubed and 2 power n, and how things become pretty bad with the 2 power n algorithm. But let me just show you a table of how time complexity changes. If you have a problem with, if you have an n cubed algorithm and you are trying to work on a problem of size 60, then that n cubed algorithm will take 0.216 second. A 2 power n algorithm will take 366 centuries. The 3 power n algorithm will take 1.3 into 10 power 13 centuries. So that is the explosion that happens with exponent, and we are only talking about problem size 60, right? You just go increase it and it's mind boggling, right? So if you have a problem of 100, 200, okay, up to n power 5 would still be reasonable, but once you get to exponential algorithm, the best known algorithms take several centuries. So, I mean, you might ask, okay, maybe this is all the power of today's computer, but if the power of the computer increases by 100 times, and today if you can handle a problem of size some 10, if it increases by 100, maybe with an n power 5 algorithm you can get, if you can handle a problem of size 100 in some 1 second, let's say, then with a 100 times faster algorithm you can handle a problem of size 2.5 times 100, okay. Whereas with the 2 power n algorithm or 3 power n algorithm, the really feasible size you can handle very, very slowly increases. So you can only handle some small number of problems in a reasonable time, okay. So here is another, so this is all from a 1970-80 book by Gary and Johnson, Computers. So this was the time when this whole notion of NP completeness was discovered, in early 70s, right. So here is another interesting cartoon from that book, that, so suppose if you come across one of these hard problems, in your company, and you try very hard, you're not able to get an efficient algorithm. What you don't want to say to your boss is that I can't find an efficient algorithm because I think I'm not clever. What would be nice is if you can go and say, I can't find an efficient algorithm because no such algorithm is possible. We don't know that as well, right? Why? Because we don't know that these algorithms really need exponential time. That is talking about a lower bound for the problem. But after learning this whole notion of NP completeness, what you can say is, I can't find an efficient algorithm, but neither can all these famous people, because this problem, by being NP hard, is equivalent to some hundreds of problems which have been tried by many experts. So at the least, your boss won't fire you and try and find somebody else, because somebody else are also struggling. Okay, so, and what more? So at the time of this 1980s book, there were 3 problems which are left open, which we did not know whether it was NP complete or polynomial time solvable. At that time, the 3 problems were primes. Given a number, is it prime? Now this has been resolved in 2004. The other problem is linear programming, right? We saw a lecture on linear programming where you want to optimize, maximize or minimize some linear objective function subject to some linear constraints. Can we actually solve linear programming in polynomial time? And this was also resolved in 80s. 80 something. So now we have a number of algorithms. Kachayan. This also has an Indian contribution. There is an algorithm due to Narendra Karmakar. There are, there's been a lot of development on this. So the popular algorithm you see for linear programming, linear programming is very old, right? 60s. The popular algorithm is a simplex algorithm, which goes through every vertex of the polyhedron region, and that is an exponential algorithm in the worst case. So linear, and whether it was polynomial time was an open problem at that time. This is resolved soon after. And the problem which is still open is the problem of graph isomorphism. This is an important problem, it has some origins in chemistry where, they were producing all these molecules which have a graph structure, and you want to know whether a new molecule that's produced is actually existing in your database or is it different. Okay. So what is the graph isomorphism problem? Given two graphs, you really want to know whether they are the same. Okay. What does it mean by same in the mathematical term? Right. So, for example, whether I draw it this way or this way, these two graphs are same. Right. Pictorially, they don't look like the same, but they are the same. How do you show it? Well, what does isomorphism means? That there exists a function. So let's say G1 is V1 E1, G2 is V2 E2, and what you want, isomorphism is a function from V1 to V2, right? For every vertex here, I should have a corresponding vertex there. That's a mapping with the property that whenever you have an edge here, the f of I1 comma f of I2 must be an edge. So a mapping here would be, for example, 1, 2, 3, 4. So if I call this is f of 1, f of 2, f of 3, is this a correct function? No, because 2, 3 is an edge here, but f of 2, f of 3 is not an edge here. Okay. These two graphs are same, they are isomorphic, but you have to give the correct function. So f of 3 is this. Clearly, there are some necessary conditions for two graphs to be isomorphic. What are some? When can you say these two graphs are not isomorphic? Some simple reasons to reject. Yeah, if the degrees are different, look at the degree sequence. If they are different, number of vertices is different, number of edges is different, but none of this is sufficient. Okay, you can have all vertices having the same degree, number of vertices, number of edges being the same. So your degree sequence may be the same, number of vertices, number of edges same, but still the graphs may not be isomorphic. Okay. So, is there a nice polynomial time algorithm to test whether two graphs are isomorphic? Is still an open problem. Is the problem in NP? You give a function and you can check this condition. So the function would be the witness, right? Give a function, that would be your witness, and you check whether this condition is satisfied. Then the problem is in NP, but we still do not know whether the problem is in polynomial time solvable. So there are a lot of special cases for which polynomial time algorithms are known. For example, if you are talking about bounded degree graphs, two bounded degree graphs, we can show that there is a polynomial time algorithm using a lot of algebra that can test whether two graphs are isomorphic, but for general graphs, it's still open.